Light that reflects at glancing angles from non-metallic surfaces like glass, water, or roads vibrates mainly on the plane of the reflecting surface. What in the world does that mean? That's polarization. Light travels in waves. The fact that waves are transverse and not longitudinal is demonstrated by the phenomenon of polarization. If you shake the end of a horizontal rope, a transverse wave travels along the rope. The vibrations are back and forth in one direction. The wave is said to be polarized. If the rope is shaken up and down, a vertically polarized wave is produced. The waves traveling along the rope are confined to a vertical plane. If the rope is shaken from side to side, a horizontally polarized wave is produced. So as you can see, obviously when the rope is shaken up and down, only waves that go up and down are going to be made. But when you shake it side to side, only waves that will go side to side are made. A vibrating electron emits a polarized electromagnetic wave. A vertically vibrating electron emits vertically polarized light. So if an electron goes up and down, then it's going to emit light that is only in the vertical plane. If the electron is vibrating horizontally, the electron is going to emit light polarized on the horizontal plane. An incandescent or fluorescent lamp, a candle flame, or the sun all emit light that is not polarized. The electrons that produce the light vibrate in random directions. So that means it's not as neat as shaking the rope up and down or shaking the rope sideways. You may have some electrons that are going up and down, while some are going sideways, some are going at an angle, some are going another angle, and just it's a whole mess of light waves that are produced. When light shines on a polarizing filter, though, the light that is transmitted is polarized. So only the light on the same plane is going to come through that filter. The filter is said to have a polarization axis that is in the direction of the vibrations of the polarized light wave. Light's going to pass through two polarizing filters when the polarization axes are aligned, but not when they are crossed at right angles. Here's a picture showing a fish in the middle of the photo. On the left, without polarization. On the right, with polarization. With polarization, you will be able to spot and therefore catch more fish. Living in Florida, this is a really big deal. Whenever you're buying sunglasses, you have your option. You can have non-polarized lenses or you can have polarized lenses. This is just one example of why polarization is useful. It helps our eyes limit the amount of mess coming into them. So we're only getting one plane of light coming in, so we get to see sharper images, better shadows. Another reason is during rain. When it's raining, light is going to bounce off of those water drops or cars that are driving, and you're going to get this big, bright, shiny glare. If you have polarized sunglasses, that glare is going to be reduced. In the rain, the light bouncing off of all of those raindrops and going everywhere is going to be reduced, so you're actually going to be able to see better. A fence analogy illustrates the effect of crossed sheets of polarizing material. When the pickets of both fences are aligned in the vertical direction, a vertical vibration can make it through both fences. So this is how polarization works. You have the polarized filter in the vertical plane, up and down plane, so light that passes along that same plane will be able to get through the polarized filter. But if you have your polarizing filter rotated 90 degrees, now it's horizontal. Well, those waves are vertically vibrating, or created by vertically vibrating electrons. So the wave is vertical. It's not going to be able to pass through the horizontal plane. Here's another example. We have angled waves coming in the top, and they go through, and this is a horizontally lined polarizing film. So only waves that are going to pass through this plane are those that are directly vertical or horizontal. As soon as we add in another angle in the bottom, we see that no light will get through. Try skipping flat stones across the surface of a pond. Stones with flat sides parallel to the water bounce, or they reflect. Stones with flat sides at right angles to the surface will penetrate the water. That is refracting. They go bloop, down. Light behaves similarly. The flat side of a stone is like the plane of vibration of polarized light. Light reflecting from non-metallic surfaces like glass, water, or roads vibrates mainly in the plane of the reflecting surface. So glare from a horizontal surface is horizontally polarized. The axis of polarized sunglasses are vertical, so that glare from horizontal surfaces is eliminated. Polarization tells us whether a wave is transverse or longitudinal. Polarization occurs for a transverse wave only. Light is transmitted when the axes of polarizing filters are aligned, and light is absorbed when they are at right angles to each other. Surprisingly, when a third filter is sandwiched between the two, light is still going to be transmitted. This explanation involves vectors, which involves more math than we will do. Why is glare from a horizontal surface horizontally polarized? You should be able to answer that.